Here for lesson 33, we're getting into a number of different probability problems. We do have a number of terms that we need to go over very quickly. So definition number one, an operation, process, or an activity in which outcomes can be used to estimate probability. That's our experiment. So maybe we're flipping a coin, rolling a die, maybe it's a spinner, you name it, but it's just an activity or a process that could estimate the probability for us. Definition number two, a process or a possible result of a probability experiment, that is your outcomes. So if we think about rolling a die, the possible outcomes that we could get are going to be 1, 2, 3, 4, 5, and 6, assuming that we're dealing with a 6-sided die. Each time that we do this, or each repetition, is going to be called a trial. So understand, more times than not, it's just going to be one trial. We're only going to roll the die once. But there's going to be cases where we do it more than once, so 2, 3, or 4 times or whatever. Example number one, a cafeteria offers turkey, ham, and chicken salad sandwiches. The bread can either be rye or wheat, therefore how many different sandwiches can be ordered here? You can think of this as a tree diagram if you want to. We have turkey, ham, and chicken salad sandwiches. But with each three of these meats, we can also have two different types of bread. So we can either have rye or wheat. And there they are. And notice, because we have two types of breads for each meat, that will get us a total of 6 different sandwiches we can make. Now, a lot of you are saying, well, we had 3 types of meats and 2 types of bread, so 3 times 2 gets us 6. And you're totally right. This leads into our multiplication principle that we will use here in a little bit. They will ask you for the sample space, and the sample space is the set of all possible outcomes of a probability experiment. So if we go back to rolling the die, okay, we know that the outcomes are 1, 2, 3, 4, 5, and 6. Well, the sample space is just the list or the set of all of those possible outcomes. So you will have to list each individual outcome if they ask you for the sample space. An outcome or a set of outcomes in a probability experiment, that is called the event. An example of this is rolling a die, and the event is getting an even number, which would be 2, 4, 6. So we could specify exactly what we want, not just the ordinary number, but maybe we want an even number or maybe an odd number, and that is specifying the event that we can get from it. One more, then we'll get into some more examples. 2 events that cannot occur in the same trial of an experiment are considered to be mutually exclusive. Okay, so again, 2 events that cannot occur in the same trial. An example of this is rolling a number die. And we want to know, okay, we want to roll a 3, but at the same time we want to roll an even number. Well, we know that 3 is not an even number, so there's no way I can get a 3 and an even number at the same time. Therefore, these 2 events are considered to be mutually exclusive. For example, number 2, we want to find the number of outcomes in each event. So we want to draw an ace or a face card from drawing from a deck at random of a standard deck. So the first thing we need to establish is just how many cards do we have in a standard deck. Well, there's 4 different suits, and we have an ace through a king, which means we have 13 different cards for each suit. So 13 times 4 tells us that we have 52 cards within our deck. Now, if we think about our aces, once again, there's 4 suits. There's hearts, diamonds, clubs, and spades. There's 1 ace of each. So in terms of the aces, we have 4. If you think about our face cards are jacks, queens, and kings. So we have 3 of each suit, and then there's 4 suits, so 4 times 3 tells us that there are a total of 12 face cards that are going to be in our deck. 12 plus 4 gets us our total of 16. Once again, if you go back and look at the wording of this problem, it's draw an ace or a face card. So we don't care which one we get as long as we get one or the other. So a total of 16 there. For B, we're looking at a prime number or a multiple of 6 or a multiple of 10 by choosing a number at random from the whole numbers 1 through 20. Okay? So once again, let's go through each of these events. Let's start with the prime numbers. If you think about your prime numbers between 1 and 20, we have quite a few of them. 1 is not considered prime or composite, so we have the number 2. We have the number 3. 4 is not prime. 5 is prime. 6 is not. 7 is prime. 8 is not. 9 is not. 10 is not. And then we have, to speed things up here a little bit, we have 11, 13, 17, and 19. So as we go to add these up, notice we have 8 of them. So in terms of getting a prime number between the numbers 1 and 20, we have 8 of them. Now let's go to our multiples of 6. Multiples of 6, we start with 6, and then we increase by 6, so we go to 12. We increase by 6 again, we go up to 18. We could go up to the next one, which is 24, but we know that that's going to be above 20, so that's all we have there in that list. We have 3 of them that are multiples of 6. And then lastly, if we look at multiples of 10, we start with 10, increase by 10, we get to 20. Therefore, we have 2 through our list of 1 through 20. Therefore, if we add 8, 3, and 2, there are a total of 13 numbers that are either considered prime, or a multiple of 6, or a multiple of 10. So be careful as you list those out. Example number 3. Getting into some better examples here, a student is choosing a 3-letter password for an email. So we have 3 letters. How many passwords are possible if letters may be repeated? So the way I like to view these is we have our 3 digits here for our 3-letter password, and we need to think about all the different choices that we have for each of these digits. Well, if we start with our very first digit, we know that there's 26 letters in the alphabet. So I have 26 different possibilities for that first one. Now, if the letters can repeat, we know that when it comes to digit number 2, we again have 26 options. And once again, 26 options for the third digit. And it is your multiplication principle. So 17,576. For part B, they're asking the same question, but now what if the letters cannot repeat? So our scheme is going to be the same, but now it's going to change slightly in terms of how many we have to choose from. For the first digit, we still have all 26 letters available to us. Now, I don't know which letter I selected for the first digit, but I do know that I selected one of them. So when it comes to my second digit, I have one less than what I had before, so now I'm down to 25 available letters. And just like with the first one, we selected one for the second, so now we've chosen 2 letters, which brings us down to 24 for the third and final digit. So that is the difference between letters repeating and not repeating. Multiply together, that means there are 15,600 options available to us. Independent events versus dependent events. An independent event really stands alone, and it does not affect the probability that's going to take place. So we don't care about what happens on the first event. Okay, if it's an independent event, we still have all of our options available to us on the second event. And then that's just the opposite for dependent events. Dependent events, it's really going to depend on what we get for the first event, and that'll dictate our possibilities for the second event. And we'll see that here in example number 4. We have the letters A through E written on 5 index cards, so 1 letter for each index card. Card is going to be chosen at random, and then another card is going to be chosen. Determine whether the events in each case are independent or dependent. So for part A, we're going to choose A, and then we're going to choose B if the first card is going to be replaced before the second card is chosen. So imagine, if you will, we have our 5 cards. We're going to choose one. We're going to look at the letter, but then we're going to replace it before we go to pick the second one. So the question becomes, does it really matter what we chose for the first one? No. As long as we put that card back into the deck, we're still going to have it available to us for the second pick. So this is a case where it's an independent event, simply because we're putting the card back into the deck. We're replacing it. And then you can about imagine B. We're going to choose A, and then we'll choose a second card B, but if the first card is not going to be replaced. So again, imagine, if you will, the 5 cards we have to choose from. We're going to choose one of the cards, but now instead of putting it back into the deck, we're going to keep it out of the deck. So when you go to choose your second card, now we're down to 4 cards. And it really does depend on what we get on that first one, will kind of dictate what we get for our second card. And that's where our dependent comes into play. Last one, example number 5. There are 6 positions on the volleyball court. We have the front left, the center front, the right front, the left back, the center back, and the right back. So think of it this way. It's going to be very much like the passwords problem. We have our 6 different positions on the court, and they're asking us how many ways can these 6 players be placed on the court. So it doesn't really matter where we start by placing these players. Let's just go ahead and start with our back left row. 6 players on the roster, which means we have 6 different options to put in that back left corner. Now once we choose one of those players, that means now we only have 5 remaining for the second position. And once we choose one there, we've chosen 2 players, so now we're down to 4, 3, 2, and then eventually we're down to our last player for that last position. If you multiply all these together, it seems like a lot, but there are 720 different ways that we can rearrange 6 players onto the court. Pretty impressive. So for your homework, I want you to go ahead and complete the practice set problems. I actually just want you to do all of them that are from lesson 33, and then we can go over those when you get back.